A fire is burning in the Everglades. It is a statement that defies logic, as swamps are, by their very nature, resistant to flames. Yet, helicopters are currently dousing the Florida sawgrass with water, as a blaze consumes 14,800 acres, with only 20% of it contained. This incident, however, is not an isolated event. It is one of 61 wildfires raging across Florida, a state where 99% of the land is experiencing drought. The crisis extends even further, as the entire United States has just recorded its most arid spring since record-keeping began in 1895, breaking a 131-year benchmark in a single month. The oceanic phenomenon fueling this situation, a potential super El Niño with parallels to a historical event that caused millions of deaths, has not yet reached its full intensity. This suggests we are only witnessing an opening chapter. The developments that should cause the most concern are still on the horizon, and we will be tracking this situation as it unfolds through December. To understand what comes next, stay with calm space. The fire is still active, the drought continues to worsen, and the oceanic engine driving this entire system is still building power. Let the fundamental reality of the situation settle in. A wetland is ablaze. This isn't a dry forest or a desert scrubland, but one of the most thoroughly water-saturated ecosystems in North America. Under normal circumstances, this environment would simply extinguish a flame. It is a landscape defined by standing water, dense sawgrass, and 10,000 years of accumulated organic matter, a combination that should render the idea of a wildfire absurd. Clearly, the Everglades is not in a normal circumstance right now. The event began on the morning of the 10th of May 2026, when a fire sparked in South Florida, along the line separating Broward and Miami-Dade counties. Located near North Chrome Avenue and Northwest 186th Street, it was designated the Max Road Miramar Fire. When it first registered with emergency services, the fire covered approximately 80 acres. This scale seemed manageable, akin to the many brush fires Florida handles annually with little public notice. But then, the situation changed dramatically. In a single operational period, as the sun came up on May 11th, the initial 80-acre fire had expanded to over 4,800 acres. This is the kind of explosive growth that fire professionals speak of with caution and precision. Their measured language often conveys a more serious reality, that the situation is no longer under their direct control. With containment estimated at just 20%, the remaining 80% of the fire's perimeter was advancing unpredictably, driven by its own momentum. Emergency managers responded with a massive mobilization. On the ground, Florida Forest Service crews worked to secure the perimeter, while Miami-Dade Fire Rescue staged along the flanks and Broward Sheriff's Fire Rescue joined the effort. Overhead, helicopters flew in a constant rotation, dropping water over a defensive line established to shield the Holly Lake community in Pembroke Pines. The priority had shifted from containing the blaze to protecting residential structures, a clear sign of the fire's dangerous proximity to a neighborhood. The scene itself was a study in contradictions. Helicopters were dropping water into a swamp because that swamp was on fire. Residents in Miramar and Weston were issued air quality alerts, advising them to seal their homes and minimize time outdoors, as the smoke had become a public health hazard. Geostationary satellite imagery from GOES East, which constantly monitors the eastern U.S., captured smoke plumes so large they were visible from orbit. On the ground, drivers on Alligator Alley, the local name for Interstate 75 through the Everglades, reported near-zero visibility, forcing them to pull over because they could not see the road ahead. This is the point where one must pause and ask the question the fire itself seems to be posing. The immediate concern is not how to extinguish it. Professionals are capably handling that task. The more profound question is, how can this be happening at all? A sawgrass prairie is not supposed to burn this way in May. Ecologically, the Everglades should not behave like a tinderbox during the second week of the 5th month. A field guide to South Florida's environment would place peak wildfire risk in late winter or early spring, at the absolute latest. May is meant to mark the beginning of the wet season, when the atmospheric systems that generate afternoon thunderstorms are supposed to be activating. This is the convective engine that makes Florida one of the most lightning-prone places on Earth. The ground should be getting wetter, not drier, and yet the helicopters, the smoke, and the fire tell a different story. The fire is undeniably real. Its 4,800 acres a testament to its power. The smoke inundating Miramar and the defensive line around Pembroke Pines are real. The families sealing their windows against the hazardous air are also real. But this fire is not the whole story. It is a symptom. It serves as a signal, a moment when a system under months, and in some ways decades, of accumulating stress finally manifests in a way that is impossible to ignore. The true narrative lies in the conditions that allowed this fire to exist, that turned a wetland into a powder keg in early May. These conditions are not merely local or seasonal. They cannot be explained away by a single weather event, a brief lack of rain, or even an unusually warm spring. Instead, they represent the leading edge of a much larger phenomenon. This force has been building quietly, deep beneath the surface of daily weather reports, in the subsurface temperatures of the Pacific Ocean, in the soil moisture readings across all 50 states, and in the atmospheric patterns now locked in place over the continent. The fire raging in the Everglades is what the front lines of a planetary scale convergence looks like when it arrives in your own backyard. So, before discussing containment, recovery, or the future for the residents of Pembroke Pines and Miramar, it is essential to understand what created this fire from the ground up. The explanation does not begin in South Florida or even in the Everglades. It begins at the bottom of the Pacific Ocean. A sequence of events, so finely calibrated and seemingly improbable, is currently unfolding, prompting scientists to use words like unprecedented and historic with notable frequency. To grasp the full weight of this moment, we must trace this chain from the depths of the ocean to the smoke now blanketing the Florida wetlands. By the end, it will become clear why a 4,800-acre fire raging in a swamp is poised to become one of the most significant stories of 2026. But the key to this entire narrative begins with the fire itself. The way this blaze is behaving, how it moves, what it consumes, and what it could become, is far stranger and more perilous than the dramatic smoke plumes visible from orbit might suggest. Part 2. The ground truth. What is most alarming about the situation in the Everglades is not the visible inferno. That statement is not meant for dramatic effect. It is a structural observation about the mechanics of this particular fire. To truly comprehend the danger, one must first understand the very ground of the Florida wetlands, a composition that remains a mystery to most people, including many who call the state home. The fire, captured in news helicopters and satellite feeds, the one generating massive smoke clouds and triggering air quality warnings, is a surface fire. It is advancing across the sawgrass prairie, consuming dry brush and, critically, the invasive vegetation that has taken root across vast stretches of the Everglades over the last century. These invaders include Melaleuca, a tree brought from Australia in the early 20th century that found Florida's climate exceptionally welcoming. It spread with such aggression that it displaced native plants and even altered the local water table. Another import, the Australian pine, has similarly established a firm hold throughout South Florida. These species are not just present, they are potent fuel. They burn intensely, creating a fire load that the native, sawgrass-dominated ecosystem would not normally support at such a density. This raises a critical question about how human intervention, even with benign intent, can inadvertently set the stage for ecological disaster. The images from above show a classic wind-driven lateral spread. The fire front advances in the direction of the wind, consuming dried grasses and brush, and producing the dense, dark smoke that has reduced visibility on Interstate 75 to near zero. On the ground, emergency crews are battling the edges of this blaze with hand tools and water. Helicopters execute continuous water drops along the perimeter near Pembroke Pines, deploying the standard playbook for wildfire suppression. But this conventional firefight is only addressing half the problem. There is a second fire, a hidden one, that helicopter crews cannot see and their water drops cannot reach. Beneath the surface of the Everglades, there is a layer of peat that in some locations extends to a depth of 12 feet. This is not soil, as most people would define it. Peat is the dense, accumulated organic residue of millennia. Over thousands of years, the sawgrass, algae, and other aquatic plants that thrived and died in the Everglades did not fully break down. The process of decomposition requires oxygen, a scarce resource in a perpetually water-saturated environment. Instead, this organic material was compressed into a carbon-rich stratum. The very foundation of this unique landscape is, in fact, a record of its own history. The carbon content of this Everglades peat is substantial, ranging from approximately 30 to 45%, depending on the specific location and depth. In the most literal sense, it is a precursor to fossil fuels, a kind of partially formed coal. It represents the Earth engaged in the slow, ancient process of creating the very material that humanity would later learn to excavate and burn for energy. When the surface conditions become sufficiently dry, causing the water table to drop and the peat layer to desiccate, this subterranean deposit becomes flammable, and when peat burns, it behaves in a manner completely alien to a surface fire. A peat fire burns underground. Once an ignition source reaches it, the fire does not erupt in flames but smolders from within, creeping slowly through the soil in all directions. It consumes the carbon layer from the inside out. This creates a perplexing challenge for firefighters, as it generates its own oxygen-starved conditions. You cannot extinguish a peat fire by cutting off surface oxygen. The only effective method is to flood the soil and saturate it completely. This requires enormous volumes of water applied over a prolonged period. A peat fire can smolder for weeks or months, persisting through rainfall events that would easily douse any surface blaze. In parts of Southeast Asia, peat fires have been known to burn continuously for years. Observations from the Southeast United States Fire Coordination Center earlier in the 2026 fire season provide a sobering precedent. Active fires in other parts of the region were seen burning 3 to 5 feet down into the duff layer, the stratum of partially decomposed organic matter that sits atop the deeper peat. A fire burning at a depth of 5 feet is an underground inferno, roughly as deep as a standard doorway is tall. But in the Everglades, where the peat layer can be as deep as 12 feet, the potential for a catastrophic ignition event is in a class of its own. An effective way to visualize this dual threat is to think of a candle. The surface fire is the visible, dramatic flame that captures all the attention and appears in news broadcasts. But the peat buried beneath that surface is the wax, the vast, hidden fuel source. If the heat from the surface fire penetrates deeply enough into a sufficiently dry peat layer, what starts as a manageable wildfire response can transform into a persistent environmental crisis that continues long after the last surface flames are out. This is the mechanism by which a temporary emergency becomes a generational problem. This leads to the one question that hangs over every official briefing, though it may not be spoken aloud yet. Just how dry is the peat right now? The answer to that question is of monumental importance for predicting what will happen next. The fire, we can all see, as dramatic as it is, could under the wrong conditions be the least of the region's concerns. What makes this question so urgent is that its answer is directly connected to the central paradox we have yet to explore. The reason a wetland is dry enough to burn in the first place. Something has fundamentally altered the availability of water in this ecosystem, and it is not a change that occurred overnight. One fire burns in the open, while the other smolders out of sight. Yet both are symptoms of the same underlying issue, and the origins of this crisis lie far beyond the borders of Florida. To understand the cause, we must pull back from the smoke and examine what the water is doing, or more accurately, what it is failing to do. Part 3. The anomaly. The presence of such a fire is profoundly disorienting because it defies the fundamental nature of the Everglades. The common perception of the Everglades as a swamp, a collection of stagnant, tree-lined pools, is a deep misunderstanding of this ecosystem. In its natural and healthy state, the Everglades is not a swamp at all. It is, in reality, a vast, slow-moving river, a sheet of water flowing gently southward, and that fact raises the most important question of all. How can a river be on fire? The Everglades ecosystem is built upon a principle hydrologists refer to as sheet flow. This unique system functions like a vast, slow-moving river, as water from Lake Okeechobee historically spread out in a thin, wide layer across the flat limestone of South Florida. It would travel south at a leisurely pace of about 1 mile per day, undergoing a natural filtration process through sawgrass prairies, tree islands, and mangrove coasts before finally meeting the ocean. In its natural state, this means the surface of the Everglades should almost always have some standing water, not necessarily deep, perhaps just a few inches, but consistently present. This fundamental characteristic makes the current situation so alarming. As of May 2026, soil moisture readings across the region are languishing between the 5th and 20th percentile. This is a clinical way of stating that the ground is drier than it has been in 80 to 95% of all previously recorded years for this same period. The standing water that should be nourishing the sawgrass, even during drier months, has vanished from areas that are now engulfed in flames. What makes this situation particularly strange is the status of Lake Okeechobee itself. This massive freshwater body, which serves as the primary reservoir for the entire Everglades system, is not experiencing a drought. In early May 2026, its water level was recorded at approximately 19.89 feet, a figure that is actually above the historical average for this time of year. The water is there. The reservoir has not been depleted. Yet, despite this abundance at the source, the surrounding land is burning. This reveals the core of the problem in South Florida, a profound system imbalance. While significant quantities of water exist in major reservoirs, its distribution and availability at the surface in the soil and the shallow water table that the ecosystem relies on is catastrophically abnormal. The roots of this crisis lie in a combination of century-old engineering decisions and recent atmospheric conditions. The natural sheet flow of the Everglades was deliberately interrupted decades ago. A complex network of canals and water control structures was constructed south of Lake Okeechobee, designed to support large-scale agriculture and to shield urban development from natural flooding. This vast replumbing of the landscape means that water, which would have naturally dispersed across the ecosystem, is now channeled through a managed infrastructure. It is moved not according to the needs of the environment, but to where human management dictates. This raises a critical question about the long-term viability of such an altered system. Under typical atmospheric patterns, this engineered imbalance is partially offset by Florida's distinct wet season. From roughly June through October, the state receives immense amounts of rainfall, which recharges the soil and replenishes the surface water. The spring months are naturally drier, but they mark a crucial transition. By May, rising temperatures usually trigger increased convective activity. causing the atmosphere to cycle water more aggressively and signaling the start of the rains. This vital transition, however, has failed to materialize this year. The expected rainfall has not arrived, leaving the system dangerously exposed. This deficit in soil moisture is not a new or sudden problem. It has been building for months, driven by a persistent pattern of atmospheric high pressure that has suppressed rainfall across the state with unusual efficiency. This high-pressure system has acted like a lid, preventing the formation of rain clouds and allowing the ground to grow progressively drier. The consequence is a managed water system that, at its surface, has been almost completely drained of moisture, creating a landscape primed for fire. The timeline for fire danger has been dramatically altered. The fire season has effectively shifted forward by approximately 6 weeks. Emergency managers report that the conditions they would normally expect in late spring or early summer arrived in the first part of May. To have operational summer conditions, from a wildfire management perspective, in the second week of the 5th month is highly unusual. This is more than just a weather event, which implies a temporary deviation from the norm. What is unfolding in the Everglades, allowing a wetland to sustain a major wildfire, is not temporary. It is the visible outcome of a systemic shift in atmospheric circulation that extends far beyond the borders of Florida. To see the proof, one only has to look at how many other fires are burning. One fire in the Everglades can be seen as a local incident. However, 61 active wildfires burning simultaneously across a single state tells a story about a system in crisis. As of the 11th of May, 2026, Florida was contending with that exact number. These were not 61 fires that had occurred over the entire spring. They were 61 separate, active fires, all burning at the same moment. The year-to-date total had already surpassed 2,000 reported fires, consuming more than 120,000 acres. The situation was so severe that 49 of Florida's 67 counties were under active burn bans, meaning over 70% of the state was officially designated as too dry for any form of open burning. Running concurrently with the Max Road Miramar fire were other major blazes, underscoring the widespread nature of the emergency. The railroad fire was burning through approximately 4,796 acres in another part of the state, while the Sargent fire covered roughly 2,523 acres. These were not minor incidents, but significant events happening at the same time as the Everglades fire, across different ecosystems and counties. The sheer scale and distribution of these fires demand that we look for a common cause. Pattern recognition is a fundamental human skill, though we often apply it too freely, seeing connections in random data, a tendency sometimes called apophenia. This has led to countless false conclusions throughout history. But there are moments when recognizing a pattern is the correct and necessary response, when the data is not random and the connections are real. Failing to connect the dots in these instances is the greater error. May 2026 inches. Florida appears to be one of those moments. The presence of 61 fires across a single state at the same time is not a case of random ignition events coincidentally clustering together. It is the direct result of a single underlying condition. Fuel, in the form of vegetation, has become dry enough to burn and is distributed across a geographic area so large that normal ignition sources are now starting fires wherever they occur, whether from lightning, human activity, or equipment sparks. Fires are igniting everywhere because the conditions everywhere are abnormally favorable for them. The science that produces a wildfire is fundamentally simple, often described as the fire triad. You need fuel, which is the vegetation available to burn. You need dryness, meaning a low moisture content in that vegetation and the soil. And finally, you need an ignition source. The critical factor in Florida's current crisis is that the first two elements of this triad, combustible fuel and extreme dryness, are now present on a statewide scale. turning what would be isolated risks into a collective catastrophe. For any fire to ignite, three components are necessary. But under typical circumstances, one of these elements usually acts as a brake on the others. While sources of ignition are frequent, the availability of fuel and an accelerant like extreme dryness are rarely so severe at the same time that every spark erupts into a major blaze. In Florida, right now, this natural balance has been broken. The state's lush, biologically productive landscape provides an abundance of fuel. Simultaneously, a drought that has intensified for months has created extreme dryness. With two parts of the equation at their maximum, there is little left to stop any ignition from becoming a wildfire. This is a critical failure, but it is the timing that is perhaps most alarming. The sheer scale and density of these fires, spanning so many counties at once, is something Florida normally associates with the peak of its fire season in late spring or early summer. Yet, we are only in the first week of May. The fire season is unfolding approximately 6 weeks ahead of schedule, a sign that the environmental system is not behaving as it should. This detail transforms a state-level emergency into the opening act of a much larger narrative. What is occurring in May 2026 is not merely a fire season. It is a systemic collapse in progress. The fires are the most visible symptom, but the system that is failing is not Florida's fire management infrastructure. It is the fundamental atmospheric and hydrological engine that keeps the southeastern United States viable. To understand how we arrived at this point, we must look past the flames and follow the path of the water, or more accurately, its profound absence. Florida is supposed to be wet. This is not just a perception shaped by vacation brochures or the memory of humid air and afternoon thunderstorms. It is a foundational aspect of the state's identity. In a typical year, Florida receives more rainfall than any other state east of the Mississippi River. Its water table is famously high, so close to the surface that sinking a well is often a simple task compared to the deep drilling required in the American Southwest. Before modern interventions, the vast Everglades system functioned as a slow-moving river, continuously pushing millions of gallons of fresh water across the continent's southern tip. Florida has never been a dry state. This deep-seated identity as a water-rich landscape is precisely what makes the current situation so jarring and paradoxical. According to the most recent assessment from the United States Drought Monitor in May 2026, an astonishing 99% of Florida is officially in a state of drought. This is not a casual description, but a formal classification based on measurable deficits in precipitation, soil moisture, groundwater, stream flow, and reservoir levels. The designation is the result of rigorous scientific analysis. A closer look at that 99% figure reveals a truly dire situation. Approximately 53.52% of the state is under a D3 or extreme drought classification. Another 24.99% is classified as D4 or exceptional drought, which is the most severe category possible. The term exceptional may sound almost positive, but in this context, it signifies conditions so severe they are statistically estimated to occur less than once every 50 years. This means that nearly a quarter of Florida is experiencing a crisis that should happen no more than twice in a century. Furthermore, this is not a recent phenomenon. Roughly 85% of the state has been in at least a severe D2 drought since the middle of February. For nearly 3 months, the situation has been continuously worsening, with no signs of recovery. And yet, within this crisis lies a perplexing contradiction. Lake Okeechobee, as mentioned earlier, is not empty. Its water level is actually above the historical average for this time of year. The state's vast network of canals, the engineered arteries that manage water flow, are also holding water. The Floridan aquifer system, one of the most productive groundwater sources in the world, is not critically depleted. This raises a crucial question. If the state's largest water storage systems are full, where is the drought? The answer lies in the distinction between stored water and surface moisture. What Florida is missing is not water in the aggregate. It is missing the active process of precipitation falling from the sky, making contact with the land, and infiltrating the upper soil layers. It is the absence of rain, the one irreplaceable mechanism that delivers water directly to the landscape in the precise distribution that ecosystems and agriculture require. Stored water in a lake is immensely useful for managing human water supplies, for urban treatment and distribution, and for irrigation provided the infrastructure exists to move it. But it cannot perform the functions of rainfall. It does not recharge soil moisture across millions of acres of forest and prairie. It does not replenish the shallow water table that determines whether a sawgrass marsh is wet enough to resist a wildfire. It does not seep into the spaces between soil particles in the Everglades, maintaining the moisture that prevents 12-foot deep deposits of carbon from becoming kindling. The tragedy is not that Florida ran out of water, but that the water is in the wrong place. The water is in the lake, while the soil is burning. The reason the sky has stopped delivering this vital moisture has nothing to do with Florida specifically, but everything to do with a persistent atmospheric pattern that has been locked in place over the southeastern United States for months. That pattern has a name, and understanding it is the key to understanding why the fires are burning. To grasp why the skies over Florida have failed, one must first understand how rainfall is generated in the southeastern United States, because the process is not as simple as many imagine. People often think of rain as a direct result of having enough moisture in the air. While technically true, this is an incomplete picture. The more critical factor is whether atmospheric conditions support the vertical movement of that moist air. In a tropical and subtropical climate like Florida's, rainfall is predominantly convective. This means it is driven by a cycle. Warm, moist air rises from the surface, cools as it ascends, and condenses to form clouds and eventually rain. For this natural process to work, however, the atmosphere above the surface must be in a state that allows, or ideally encourages, that upward motion. The atmospheric instrument that suppresses this vital process is high pressure. At its core, a high-pressure system is a vast column of descending air. As this air sinks toward the ground, it spreads outward. The physics of this process are immutable. Descending air warms and dries as it falls. This creates a stable, heavy layer that acts like a lid on the lower atmosphere, effectively trapping the warmer, moisture-laden air near the surface and preventing it from rising. This suppression of vertical movement is the direct cause of the clear, sunny, and rainless days that have plagued the region, turning a normally vibrant landscape into a tinderbox. A lack of rainfall is rarely a passive occurrence. More often, it is the result of an active force working against the very mechanics of weather. When a powerful high-pressure system settles over an area, it doesn't simply fail to create rain. It actively stifles the atmospheric processes that would otherwise generate it. In the spring of 2026, the feature responsible for this suppression over Florida and the American Southeast is an atmospheric phenomenon known as the Bermuda High. This semi-permanent circulation pattern over the North Atlantic, also called the North Atlantic Subtropical High, typically has a positive effect on the region's weather. Under normal circumstances, its western edge sits offshore, helping to guide tropical moisture northward along the coast and contributing to rainfall. But when the Bermuda High strengthens and shifts unusually far to the west, it positions itself directly over the southeast, effectively placing a lid on the atmosphere. This prevents the warm, moist surface air from rising, halting the convective process that generates Florida's characteristic afternoon thunderstorms. The result is a dramatic drop in precipitation. This is precisely the scenario that has been unfolding. Over the spring, Rainfall deficits across the region have reached 8 to 16 inches below normal. In certain areas, such as the Interstate 10 corridor in the northern Gulf states, the long-term deficit is a staggering 20 to 30 inches. To put that into context, a deficit of 20 to 30 inches is equivalent to the entire annual rainfall of some semi-arid parts of the American West. The direct consequence in Florida is a collapse in soil moisture, which has created the perfect conditions for these fires. Current readings in the 5th to 20th percentile indicate that the soil has lost nearly all of its typical water content. The thin layer of moisture that normally saturates the upper levels of the Everglades ecosystem, the water that keeps the sawgrass too wet to burn, and the peat layer resistant to combustion has simply evaporated, with no rain to replenish it. The troubling detail, however, is that this is not merely a Florida problem. The anomaly in the Bermuda High that is choking off rain in the southeast is a symptom of a much larger disturbance in the atmospheric circulation. A persistent ridging pattern has fundamentally reorganized the flow of weather systems across the entire North American continent. Evidence of this reorganization can be seen in drought data from states far from Florida's borders. Florida is simply the place where we can see the fire most clearly, as it represents the most flammable endpoint of this continental atmospheric shift. But the system driving that fire is continental in scale. The proof of this is found in a number so stark that it warrants its own discussion. What is happening in Florida is, in fact, happening simultaneously across most of the country. To truly grasp the magnitude of this event, one must look at what the United States Drought Monitor recorded for the spring of 2026 and understand its significance within the 131-year record. Before we zoom out to that continental picture, there is another critical aspect of the Everglades fire that must be understood as it connects this local event to a global story. From a climate perspective, the fundamental characteristic of peat is that it stores carbon. Peat forms when organic matter accumulates more quickly than it decomposes, a process common in waterlogged environments. Over thousands of years, this can lead to vast deposits of stored carbon. The peat layer of the Everglades is not just a fire risk, it is a massive carbon reservoir. It is a natural vault where millennia of atmospheric carbon have been sequestered through biological processes, operating on timescales that dwarf human history. When that peat burns, the carbon does not just vanish. It is released back into the atmosphere as carbon dioxide and methane. A fire lasting only weeks or months can reverse a sequestration process that took thousands of years to build. We have sobering historical precedents for what this looks like on a large scale. In 1997, during a severe El Niño drought, peat fires in Indonesia burned through drained and degraded peatlands, releasing an estimated 2 to 9 gigatons of carbon. To appreciate this figure, consider that global fossil fuel emissions at the time were approximately 6 to 7 gigatons per year. In a single event, the Indonesian peat fires may have emitted as much carbon as all of humanity's fossil fuel consumption for that entire year. Then, in 2010, another series of peat fires broke out in Russia during an extreme heat wave. The smoke was so dense, it triggered health emergencies in Moscow and led to an increase in cardiovascular deaths across a wide area. These events serve as reference cases for what the ignition of the Everglades peat on a major scale could entail. The carbon reservoir beneath South Florida is not insignificant. If it were to experience sustained combustion during an extreme drought, the result would not be a local air quality issue. It would be a regional climate feedback event. For now, this remains a risk, not a certainty. As of the 11th of May, 2026, there is no evidence that widespread, deep combustion has begun in the areas affected by the Max Road Miramar fire. What has been confirmed is a surface fire moving across a wetland that should be too damp to support it. But the reason this risk is so significant, and why it must be included in any honest assessment of the situation, is that it ties directly back to the central question. The fire in the Everglades is a signal. It demonstrates that the necessary conditions for something far worse are now in place. The peat below the surface is not yet burning, but the surface fire above it exists precisely because the conditions that could ignite the peat, prolonged extreme drought, suppressed rainfall, and depleted soil moisture, are already fully established. The surface fire is the warning. The peat is what it is warning about. And both of these facts can only be fully understood by examining the continental scale of the drought that created them. At this point, someone intimately familiar with Florida's fire history might offer a note of reassurance. They might point out that Florida has burned before, citing past events with record-setting fires that make the Max Road Miramar incident seem modest in comparison. That person would be correct, and that historical context is indeed important. In 1998, a series of devastating blazes, known as the Florida firestorm, scorched approximately 500,000 acres of the state and led to the evacuation of over 120,000 residents. The fires moved with a speed and ferocity that overwhelmed local resources, necessitating federal disaster declarations. Other major events followed, including the 2007 Bugaboo Complex fire, which burned over 500,000 acres in Florida and Georgia, and the 2011 Honey Prairie fire, which smoldered for nearly a year. These events reveal a fundamental truth. Florida is a state defined by fire. This reality is driven by a predictable, recurring cycle. Wet years, often fueled by active hurricane seasons, encourage lush vegetation growth. When cyclical droughts inevitably return a pattern historically linked to El Niño events in the Pacific, this accumulated plant matter becomes tinder, setting the stage for dramatic fire seasons. The connection between Pacific El Niño events and Florida's fire risk is well documented. El Niño's influence on atmospheric circulation typically reduces winter and spring rainfall in the region, creating the dry conditions that precede the state's primary fire season in late spring and early summer. The catastrophic 1998 firestorm, for instance, occurred just as the powerful 1997-98 El Niño was subsiding, a correlation that was far from coincidental. In this context, a severe fire season during an El Niño year is not surprising. It follows an established script. What is profoundly different in 2026, however, is the timing. With 2,000 fires reported by early May and 61 burning concurrently in the second week of the month, the fire season is running 6 weeks ahead of schedule. This density of fire activity is what experts would normally expect in late June or July. The entire calendar has been shifted forward in a way that historical patterns cannot easily explain. Even more perplexing is the fact that the conditions of 2026 are not appearing at the end of an El Niño cycle, as they did in 1998. Instead, the drought and fires are manifesting times before the El Niño has even fully formed. This anomalous dryness across the southeastern United States is not the typical aftermath of a Pacific climate phenomenon. It seems to be a precursor. This departure from the established sequence suggests that something is occurring within the atmospheric system that the traditional El Niño playbook fails to account for. The key to unraveling this puzzle is not found in Florida's climate alone, but in the precipitation records for the entire continental United States. The story of this data begins in 1895. This year marks the start of systematic, standardized national precipitation monitoring by the US government, an initiative of the Weather Bureau, which would later become the National Weather Service. For 131 years, through every conceivable weather extreme, the North American continent could produce from dust bowls to deluges. These meticulous records have been maintained. They provide an invaluable baseline against which modern events can be measured. and the measurement for 2026 is alarming. The numbers from the first quarter of the year paint a stark and unambiguous picture. Between January and March of 2026, the contiguous United States received an average of only 4.79 inches of precipitation. This is less than 70% of the historical average for that same period. More significantly, it is the lowest 3-month precipitation total for the start of a year ever recorded since the dataset began in 1895. This isn't merely the driest start in recent decades or since the Dust Bowl. It is the driest in the entire 131-year history of systematic monitoring. This is a record of profound significance. But the data reveals even more. The Palmer Drought Severity Index, a standard scientific metric for drought intensity, registered a nationwide average of -7.84 for March 2026. On a scale that runs from roughly +10 for saturated conditions to -10 for absolute dryness, a reading of -7.84 falls deep into the territory of extreme drought. It also stands as the most severe national reading ever recorded since the index was developed and retroactively applied to the historical data. In a single month, 2 critical records measuring the same phenomenon from different perspectives were broken. In the opening months of 2026, the United States was drier than at any other point in the modern instrumental era. When scientists describe an event as historically unprecedented, they do so with a clear understanding of the statistical weight of that phrase. To break a record in a dataset spanning 131 years suggests that the underlying cause is not just unusual, but is instead an outlier of an extreme nature, something the climate system had not produced during the entire observation period. This forces us to consider that the conditions driving this outcome may be qualitatively different from anything in the modern record. By the spring of 2026, 60% of the contiguous United States was officially in drought, a geographic extent 3 times the typical 30%. The fires in the Everglades are a direct consequence of this reality. They are the local expression of a continental-scale atmospheric anomaly. This understanding leads to the essential question the data demands. What could cause the worst drought since record-keeping began? The answer appears to have 2 distinct parts. One component is a persistent drought system that has been intensifying in the American West for over 2 decades. The other is a new and powerful phenomenon that seemed to arrive almost overnight. When climatologists examine the drought map of spring 2026, they do not see a single, uniform event. Instead, they identify 2 separate drought regimes, born from different atmospheric mechanisms that are now overlapping. This convergence has created a compound condition where the 2 systems amplify each other's effects, leading to a situation far more severe than either would be alone. The first of these is the Western drought, a crisis 22 years in the making. Scientists refer to the water crisis affecting the American Southwest as a megadrought, and this is not an overstatement. Based on multiple paleoclimate reconstructions using tree rings and other proxy data, researchers have confirmed that the drought impacting the Colorado River Basin, the Great Basin, and surrounding states since the early 2000s is the most severe the region has experienced in roughly 1,200 years, after a millennium of fluctuating wet and dry periods. The 22 years leading up to 2026 represent the most profound and sustained water deficit in 12 centuries of climate records. This is not a new event that began in 2026. It is a slow-moving catastrophe that has been unfolding for decades, fundamentally altering the hydrology of the western United States. It has steadily depleted the Colorado River and its reservoirs, forcing a re-evaluation of agriculture and water policy across 7 states. The disaster has progressed on such a long timescale that, for many, it has become almost invisible, a crisis normalized by its own persistence. In stark contrast to the slow-burn megadrought in the West, a second drought appeared in the southeastern United States, almost without warning. The technical term for what struck the region in the first months of 2026 is a flash drought. This concept, formalized by researchers like Jason Otkin and his colleagues over the last decade, describes a phenomenon fundamentally different from the gradual development seen out west. A flash drought is defined by its rapid onset, materializing over weeks rather than months or years. Its primary driver is not a long-term precipitation deficit, but a destructive combination of unusually high temperatures, low atmospheric humidity, and persistent atmospheric blocking patterns. Together, these factors can drain moisture from the soil so quickly that conventional early warning systems, which rely on rainfall deficits, simply do not have time to register the threat. It raises the question of how we prepare for a disaster that arrives with such alarming speed. The events in North Carolina during 2026 provide a clear and sobering example of a flash drought's velocity. County-by-county data revealed the region plunging from normal conditions into severe and even extreme drought classifications in a matter of weeks. Forecasters describe this rate of decline as one of the most rapid drought development events ever observed for a major populated area. To track this kind of swift desiccation, scientists rely on a specific instrument, the Evaporative Stress Index, or ESI. This index measures the disparity between the amount of water the atmosphere could evaporate under current temperature and energy conditions, and the amount it is actually evaporating from the land surface. When a large gap appears, meaning the atmosphere is thirsty for far more water than the ground can provide, it serves as a leading indicator of a developing flash drought. This powerful tool tells us that the land is losing its moisture to the sky faster than it can be replenished. Throughout the spring of 2026, the ESI across the southeast was, in scientific terms, screaming a warning. What makes this double drought scenario particularly significant for understanding the fires in the Everglades is that the western megadrought and the southeastern flash drought are not entirely separate events. They are both consistent with a specific atmospheric circulation pattern, the formation of a persistent high-pressure ridge over the central and western United States. When this ridge is strong, it simultaneously blocks precipitation in the areas directly beneath it, while diverting storm tracks away from regions that would normally receive rainfall. The emergence of two distinct drought regimes across the United States in 2026 was not a mere coincidence. Instead, it represented two different expressions of the same underlying atmospheric reorganization. The question of what is driving this large-scale shift has a partial answer in atmospheric dynamics. But a deeper explanation lies in the ocean. Before turning to the ocean's role, however, it is essential to understand one more atmospheric component. We must first examine the mechanism that allowed this atmospheric reorganization to become self-reinforcing, making it highly resistant to normal, day-to-day weather variability. The conventional idea of a drought, the one most of us hold, is of a slow, gradual process. It involves months of below-average rainfall, reservoirs that slowly recede, and agricultural conditions that worsen incrementally over time. The classic image is of cracked earth, a landscape shaped by a long, patient season of absence. A flash drought, however, is something else entirely. It is a climatological ambush. Its mechanism is powered by a feedback loop involving temperature, soil moisture, and the atmosphere itself. When an unusual heat event occurs, often driven by the kind of persistent high-pressure ridge seen over Florida, the elevated temperatures dramatically increase the rate at which the atmosphere pulls moisture from the soil via evaporation. At the same time, the heat forces plants to increase transpiration, the process of drawing water from the ground and releasing it as vapor through their leaves. These combined processes deplete soil moisture far more rapidly than a simple lack of rain ever could. As the soil begins to dry out, a critical secondary feedback is triggered. This reveals how the land itself can begin to conspire against its own recovery. Wet soil absorbs incoming solar radiation and uses a significant portion of that energy to evaporate water, which is a cooling process. Dry soil, however, lacks the moisture for evaporation. Consequently, it converts more of the sun's energy into what is known as sensible heat, meaning the ground and the air directly above it become substantially hotter. This additional heating further increases the atmosphere's demand for moisture, accelerating the depletion of any water that remains in the soil and creating a vicious cycle of heat and dryness. The final piece of this feedback loop is the atmospheric blocking pattern. When a high-pressure system stalls and becomes locked in place over a region, it isn't just a passive absence of rain. It acts as an active barrier, physically obstructing the normal progression of weather systems that would otherwise disrupt the dry spell. The jet stream, the high-altitude river of wind that steers weather in the mid-latitudes, is forced to bend around this blocking high. As a result, storm systems that might have delivered crucial rainfall are rerouted to the north or south, leaving the blocked region entirely untouched. This blocking behavior is associated with a phenomenon that atmospheric scientists call quasi-resonant amplification. This occurs when the planetary scale waves that typically travel around the globe become stationary. They simply stop moving and lock into position. When these waves get stuck, the weather patterns associated with them become stuck as well. The consequences are stark and immediate. Hot regions stay hot, and dry regions stay dry, locking extreme conditions in place for extended periods. Academic studies of quasi-resonant amplification, spurred by catastrophic events like the 2010 Russian and 2003 European heatwaves, indicate that this type of atmospheric locking is growing more common as the global climate warms. The proposed mechanism behind this phenomenon stems from a weakening temperature gradient between the equator and the poles. As the Arctic warms faster than the tropics, the jet stream's behavior is altered, creating conditions that favor the development of stationary, amplified wave patterns. This suggests that what appears to be a random weather event is actually part of a much larger, more predictable pattern. In short, the conditions that enabled the Everglades fire are not a product of chance. They are the result of an atmospheric system that has become stuck, resisting the natural variability that would normally disrupt a drought by delivering rain. Florida is burning because the atmosphere overhead is locked in place. And this atmospheric paralysis is driven by dynamics that trace all the way back to the ocean, specifically to what is unfolding in the deep waters of the tropical Pacific. In every meaningful way, the fire in the Everglades is downstream from the Pacific Ocean, and the ocean's current state is arguably the most critical element of this entire story. Part 12. The heat dome continuity. Earlier in 2026, before the fire emergency in Florida captured headlines, a different atmospheric phenomenon was drawing considerable attention from meteorologists. A bicoastal heat dome event settled over the United States, with high-pressure systems generating unusual warmth on both the west and east coasts simultaneously. This kind of concurrent bicoastal heat is quite rare in the historical record. Typically, the atmospheric dynamics that produce a heat dome in the west tend to create the opposite effect in the east. The mechanism capable of generating simultaneous warmth on both coasts involves the amplification of what are known as Rossby waves. These are vast, planetary-scale undulations in the atmospheric circulation, resulting from the interplay of Earth's rotation and the differential heating between the equator and the poles. When Rossby waves amplify significantly, they form high-amplitude ridges and troughs. A large ridge in the west and a secondary one in the east can produce anomalous warmth in both regions, while the deep trough between them funnels cold air into the center of the continent. But what could cause these planetary waves to behave in such an extreme and unusual way? The connection between this kind of amplified Rossby wave pattern and the formation of drought is direct and powerful. The high-pressure ridges actively suppress rainfall, while also increasing evaporative demand on the landscape. When these amplified waves slow down or become stationary, the resulting weather patterns become persistent, transforming a weather system that would normally move on. This distinction is crucial for understanding how a region can be pushed from temporary dryness into a state of severe, long-term drought. The difference between a heat event that lasts for a week and one that stretches for a month is not primarily about the initial temperature anomaly. Instead, it is a matter of whether the atmospheric wave pattern supporting it remains locked in place or continues its natural progression across the globe. The heat dome events from earlier in 2026 were not isolated incidents. They were part of a continuous pattern of atmospheric behavior that had sustained persistent high-pressure ridging over key areas of the United States for months. The drought that led to the 1-3-1-year precipitation deficit was not the result of a single weather event. It was forged over months of this persistent atmospheric state, which repeatedly blocked rainfall, enhanced evaporation, and methodically created the conditions that now fuel 61 separate fires across Florida. The narrative of this disaster, then, is not one of sudden crisis, but of a slow, creeping accumulation of risk. Research published in the years prior to 2026 had already identified an increasing frequency of these persistent, extreme events in both observational records and climate model projections. The physical basis for this trend involves the quasi-resonant amplification mechanism, along with additional feedbacks tied to the overall warming of the climate system. The critical connection for the story of the Everglades fire is this. The atmospheric pattern that produced the bicoastal heat events earlier in 2026 and the pattern currently maintaining the drought over Florida are related expressions of the same large-scale circulatory shift. They are not separate stories, but sequential chapters in the same narrative, and that narrative has a powerful driver, one that sits not in the atmosphere but deep beneath the surface of the Pacific Ocean, where water temperatures have been building towards something extraordinary for months. Part 13. The Subsurface Reality. Most public and media conversations about ocean temperatures in the context of climate events center on the surface. Surface temperatures, anomalies measured in the upper few meters of the ocean, are what get reported in the news and appear in standard El Niño monitoring products. This is because surface temperatures are what satellites can easily measure, providing the data for daily and weekly updates from agencies like NOAA. But this is not the full picture. It is not even close. The ocean is not a shallow pool. In the tropical Pacific, the critical region for monitoring El Niño, the ocean is several kilometers deep in places. The dynamics that drive this powerful climate pattern are not purely surface phenomena. They involve the behavior of the ocean through its entire depth, particularly the thermocline, the boundary layer separating the warm surface water from the cold, deep water below. These dynamics also involve subsurface temperature anomalies that propagate across the ocean basin as vast waves of warm or cold water. In the months leading into May 2026, subsurface temperature readings in the tropical Pacific were revealing anomalies that, depending on the depth and location, reached as high as +8 degrees Celsius above the climatological average. To put that number into perspective, the extreme El Niño events that climatologists consider the strongest in the modern record, those of 1997, 98, and 2015-16, produced subsurface anomalies in the range of +4 to +6 degrees Celsius. Readings approaching +8 degrees signify conditions that fall outside the entire envelope of the strongest events in the modern observational record. This data forces us to reconsider the very definition of an extreme event, suggesting the climate system is beginning to operate under rules we have not witnessed before. A key indicator of the heat stored within the ocean system can be found at a depth of 300 meters, where temperature anomalies are closely monitored. This stored energy can eventually surface, influencing both surface temperatures and atmospheric circulation. At this depth, readings were showing temperatures approximately 1.6 degrees Celsius above the mean. While that number may seem small compared to anomalies at the surface, it represents a colossal amount of energy when applied to such an immense volume of water. The question, then, is how this deep, hidden warmth translates into weather patterns felt in places like Florida and across the entire continental United States. The answer lies in a mechanism oceanographers refer to as Kelvin waves. These are vast pulses of warm water that travel eastward across the equatorial Pacific, both at the surface and deep below. They carry anomalous heat from the western Pacific warm pool all the way to the coast of South America. As a Kelvin wave completes its journey across the basin, the warm water it transports arrives at the eastern edge of the Pacific. There, it disrupts the natural upwelling of cold, deep water that normally keeps the eastern Pacific cool. When this upwelling process is suppressed, surface temperatures begin to climb, and an El Niño is born. In the months leading up to May 2026, scientists had documented a succession of these Kelvin wave pulses crossing the equatorial Pacific, each one depositing more anomalous heat in the east. The subsurface temperature readings were a direct reflection of the cumulative impact of these waves. As warm water gathered in the central and eastern basin, building toward its eventual expression as an El Niño. This buildup of oceanic heat led climate scientist James Hansen, whose research has often preceded the scientific consensus, to make a stark declaration. He stated that the development of a significant El Niño event in 2026 was, in his view, effectively assured. This was not a statement of probability or likelihood, but of certainty. Such language reflects the conclusion of a scientist who has examined the subsurface data and determined that the physical process was too far advanced for normal atmospheric variations to halt the outcome. In essence, the ocean had already made its decision. The atmosphere was simply responding to a loading process set in motion months earlier. This perspective reframes the fires in the Everglades, the drought affecting 60% of the United States, and the 131-year precipitation record not as random events, but as the atmosphere's early reaction to an ocean that has already embarked on a new course. The story of this unfolding crisis begins with an event that went almost entirely unnoticed. In April 2026, something occurred in the western tropical Pacific that barely caused a ripple in mainstream news, with coverage confined mostly to meteorological blogs and specialized climate publications. It was an event without dramatic visuals, making its significance difficult to convey to a general audience. This event was a westerly wind burst. These are periods typically lasting 1 to 3 weeks, where the normal trade winds, which blow from east to west across the equatorial Pacific, reverse and blow from west to east. Under normal conditions, the trade winds act like a conveyor belt, pushing warm surface water toward Indonesia and Australia, which keeps the eastern Pacific relatively cool. A westerly wind burst interrupts this cycle, pushing that accumulated warm water back toward the east. More importantly, the transfer of momentum into the ocean's surface generates downwelling Kelvin waves, the very pulses of deep, warm water described earlier. The westerly wind burst, documented in the western equatorial Pacific during April 2026, was notable for its unusual intensity. The mechanism behind this powerful burst was a rare and potent atmospheric alignment. Its origin was traced to 3 simultaneous tropical cyclones that had formed in a coordinated pattern around the western Pacific warm pool. The interaction of their powerful wind fields generated a burst of westerly wind that was significantly stronger than what one or even two cyclones would typically produce. This rare confluence of three organized tropical cyclones resulted in an anomalous transfer of momentum directly into the ocean's surface. For climate scientists, the resulting downwelling Kelvin wave was a clear and ominous signal. It was officially classified as a strong ENSO precursor, meaning it shared the characteristics of subsurface events that have historically preceded the most powerful El Niño events on record. The 1997 El Niño, which remains the benchmark for a strong event, was itself preceded by a series of westerly wind bursts in the western Pacific in late 1996 and early 1997. The April 2026 event displayed notable structural similarities to those very precursors, suggesting history was poised to repeat itself. This illustrates a profound truth about our planet's interconnected systems. The subsurface heat building in the tropical Pacific, the engine driving the atmospheric reorganization that led to the 131-year drought record, and the Everglades fires received a significant push in April from a discrete event that remains largely absent from public discourse. A clear chain of causality connects three tropical cyclones in the western Pacific to an unusual westerly wind burst, which generated a downwelling Kelvin wave. This led to subsurface temperature anomalies approaching 8 degrees Celsius, a reorganization of the Walker circulation, a persistent high-pressure ridge over the United States, a 131-year drought record, 61 active wildfires in Florida, and, ultimately, the smoke rising over Pembroke Pines on the 11th of May in 2026. The fire in the Everglades was the downstream consequence of a chain that began with an event in a different ocean, on the other side of the planet, that most people never even heard about. With the ocean's course seemingly set, attention turned to the forecasts, which began to paint a startling picture. The ensemble model predictions for the 2026 El Niño development started showing numbers that would have seemed implausible in any other context. The strength of an El Niño is primarily measured by sea surface temperature anomalies in a specific part of the central and eastern equatorial Pacific, known as the Niño 3.4 region. An El Niño is officially declared when this region shows a positive anomaly of at least 0.5 degrees Celsius. An event is considered moderate when it reaches 1 to 1.5 degrees, while a strong event, like the one in 2015, 2016, peaks at approximately 2 to 2.5 degrees. To understand the gravity of these new forecasts, we must look at the historical benchmarks. The historic 1997 to 1998 event, which remains the standard reference case for a truly powerful El Niño, peaked at an anomaly of approximately 2.5 degrees Celsius. For decades, this figure has stood as the upper boundary of the modern observational record, defining the very limit of a super El Niño's strength. It was this established record that the new forecasts were beginning to challenge. In early May of 2026, a remarkable consensus began to form among climate forecasters regarding the Niño 3.4 region of the Pacific Ocean. Multi-model ensemble projections showed a median warming of approximately plus 2.7 degrees Celsius for the upcoming December to February period, which is historically when El Niño events reach their maximum strength. Some individual model runs, representing the upper boundaries of scientific uncertainty, even simulated anomalies as high as plus 3.3 degrees Celsius. What stood out, however, was the forecast from the European Centre for Medium-Range Weather Forecasts, or ECMWF, which operates one of the world's most advanced prediction systems. In an unprecedented show of agreement, 100% of its ensemble members, every single one, predicted the formation of a super El Niño. This kind of unanimity is almost unheard of in climate forecasting for a period 6 to 9 months out, a time frame typically dominated by atmospheric chaos and wide model disagreement. When all models align, it suggests the underlying signal is so powerful that it overwhelms the usual background noise of uncertainty. This powerful signal was echoed by other agencies. As of early May, NOAA's own assessments placed the probability of El Niño development at 61%, with the likelihood of a significant event running far above historical averages. While the models painted a dramatic picture, the scientific community was still debating the ultimate peak strength of the coming event. Some researchers, like Hansen, pointed to subsurface ocean data and a recent wind burst in April as evidence for a potentially record-shattering event. On the other hand, more conservative analysts urged caution, highlighting the inherent uncertainties in any long-range forecast and noting that atmospheric feedbacks could potentially moderate the event, keeping it below the most extreme projections. Yet, the most notable aspect of the scientific discourse in May 2026 wasn't this disagreement over magnitude. It was the extraordinary agreement on the direction of change. The consensus was clear: El Niño was coming. The only remaining questions were how strong it would be and precisely when it would peak. To grasp the potential magnitude of this event, scientists began drawing comparisons to the most powerful El Niños of the modern era, the events of 1997, 98, and 2015-16. These two episodes represent the strongest such phenomena in the instrumental record. A few researchers even looked further into the past, examining paleoclimate records reconstructed from proxy data, which pointed to a colossal event in 1877-78. But these numerical forecasts and historical comparisons, focused on sea surface temperature anomalies, fail to capture what an El Niño of this scale actually feels like on the ground. The raw data does not easily translate into the lived human experience of its consequences. To truly comprehend what was unfolding, it became clear that one had to understand a critical flaw in the public perception of its timing. This reveals a common misconception in the coverage of drought and fire, one that fundamentally inverts the timeline of cause and effect. The standard, textbook narrative of an El Niño is clean and simple. It begins in the spring, as warm water gradually accumulates across the central and eastern Pacific. The atmosphere responds slowly at first, but by late summer and into the fall, the entire system reinforces itself and strengthens. According to this model, the event reaches its peak sometime between December and February, and only then do the most severe impacts arrive. Widespread drought patterns, massive shifts in rainfall, a spike in global temperatures, and major disruptions to agriculture and ecosystems. In this framework, El Niño is like a great wave building far offshore. You can see it forming months in advance, but its full force doesn't crash upon the land until much later. According to this conventional model, May of a developing El Niño year should be a period of relative calm. One would expect to see only subtle hints of the coming event: slightly warmer sea surface temperatures, minor shifts in trade winds, and perhaps some early atmospheric anomalies visible only to scientists analyzing the data. The expectation is one of lag, where the ocean leads, the atmosphere follows, and the tangible impacts on land trail behind by several months. In short, May should have been the quiet build-up phase, but the reality on the ground in 2026 bore no resemblance to this orderly sequence. Instead of subtle signals, the world was already witnessing extremes. The United States had just experienced its driest January to March period since national record-keeping began in 1895, the driest in over a century. Simultaneously, the Palmer Drought Severity Index, a comprehensive measure that integrates both temperature and precipitation, fell to its most severe March reading ever recorded. Across the American Southeast, drought coverage was nearing total saturation. In Florida, a state practically defined by its humidity and abundant water, approximately 99% of the land was officially under drought conditions, with large areas experiencing the most extreme categories of dryness. This profound dryness, in turn, created the conditions for an equally severe threat: fire. It wasn't a single, isolated incident, but a swarm of 61 active wildfires burning across the state at the same time. Among them was a rapidly moving fire in the Everglades, an ecosystem that, under normal circumstances, should be resilient to such events. This blaze advanced through sawgrass and brush, threatening communities along the border of Broward and Miami-Dade counties. The smoke grew thick enough to reduce visibility on major highways, as helicopters dropped water on a landscape that, in theory, should already be saturated. These are not the subtle precursors of a distant event. They are not faint signals that something might occur later in the year. These are full-scale, devastating impacts, the kind of conditions that, in the standard El Niño timeline, are associated with a mature or peaking event. Yet, according to nearly every major forecast and observational metric, the El Niño itself had not yet reached that stage. It was still in its developmental phase. This creates a profound paradox. How can the consequences of an event arrive before the event itself has fully formed? How can we be experiencing disruptions characteristic of a peak phase when the system responsible has not yet peaked? The resolution to this paradox lies in a more nuanced understanding of how the atmosphere actually functions. It is a far more dynamic and responsive system than the simplified linear timeline suggests. The atmosphere does not simply sit idle, passively waiting for the ocean to complete its warming cycle before it finally begins to react. The connection is much more immediate and complex, a reality that was playing out with devastating consequences. The climate system reacts almost as soon as its underlying conditions begin to change. As the waters of the equatorial Pacific grow warmer, even during the earliest stages of an El Niño's development, this warming starts to interfere with the Walker circulation. This is the vast, east-to-west atmospheric pattern that typically governs weather throughout the tropics. Under normal circumstances, this circulation is driven by a predictable cycle of warm water and rising air in the western Pacific, balanced by cooler, sinking air in the eastern Pacific. But as ocean temperatures climb in the central and eastern Pacific, that delicate equilibrium weakens and starts to shift. This atmospheric reorganization doesn't wait for the system to reach its maximum strength. It begins early. Once this process is initiated, its influence propagates outward through the atmosphere via what are known as teleconnections. These are essentially long-distance linkages that permit changes in one part of the climate system to affect weather patterns thousands of kilometers away. A critical pathway for this influence is the Pacific North American Pattern, or PNA. This atmospheric configuration consists of a series of pressure anomalies that effectively connect the tropical Pacific Ocean to the circulation of air over North America. When the Pacific starts to warm as El Niño develops, the resulting shifts in atmospheric convection alter the path and intensity of the jet stream over the North Pacific. This, in turn, reshapes the flow of air across the entire continent. In the current setup, this reshaping appears to be encouraging the formation of persistent high-pressure ridges over large areas of North America. Such systems are characterized by sinking air, which leads to clear skies and suppresses precipitation. When these high-pressure systems become stationary or slow-moving, a phenomenon meteorologists sometimes call a locked pattern, they can trigger prolonged periods of unusual heat and dryness. This atmospheric chain of events is what truly matters in the present moment. The focus should not be on the peak El Niño months, which are still in the future, but on this early phase of reorganization, where the ocean is already exerting its influence on the atmosphere long before the full surface signal has matured. It is this initial shift that has the power to generate drought conditions, divert storm tracks, and reduce rainfall across regions that are highly sensitive to such changes. What we are observing now seems to be a direct consequence of this process. The record-breaking drought conditions unfolding across the United States do not appear to be random occurrences. The nearly complete coverage of drought in the Southeast is not merely an isolated regional issue. The fires in Florida are not simply the product of local ignition sources or brief weather fluctuations. Instead, they are all consistent with a much broader atmospheric pattern, one that has already been shaped by a warming Pacific Ocean. In other words, the climate system is already responding to these initial changes. This perspective reframes the Everglades fire in a way that most surface-level analysis fails to capture. It is not just a fire burning through a dry section of land. It is a direct manifestation of a large-scale atmospheric shift that was set in motion by changes in the ocean, the profound dryness that allows the fire to spread so readily, the absence of surface water in an ecosystem naturally designed to retain it, and the persistence of conditions that hinder recovery. All of these are downstream effects of a system already in transition. Crucially, these developments are taking place before the El Niño event has even approached its peak. This timing is the most critical detail. If the conditions we are currently experiencing represent the early atmospheric response while the system is still gathering strength, then they are not the main event. They are merely the leading edge. To fully appreciate why this distinction is so important, it is useful to consider the difference between a signal and a culmination. A signal indicates that something has begun, whereas a culmination signifies that it has reached its maximum expression. At this moment, what we are witnessing across the globe looks far more like a signal. The complication, however, is that the magnitude of this signal is extraordinarily large. It is not a subtle warning. It cannot be easily dismissed. It has already produced conditions that have broken records that have been in place for more than a century. This reality raises a question that is difficult to ignore. If a developing El Niño, still months away from its peak, is already associated with the most severe spring drought in over 130 years, widespread fire activity in a state that is typically rich in water, and atmospheric patterns that recall major historical climate events, what will happen when the system finally reaches its full strength? Historically, the peak phase of a strong El Niño is when its global influence becomes most pronounced and widespread. That is the period when rainfall patterns shift dramatically across the globe. It is when some regions are inundated with flooding, while others descend deeper into drought. It is when global average temperatures tend to spike, and when the cumulative effects of months of atmospheric reorganization fully manifest themselves. We are not at that stage yet. The effects we are seeing now, the droughts, the fires, the atmospheric locking patterns, are all consistent with the early stages of that larger process. They represent the system beginning to reorganize itself in response to changing ocean conditions. However, the ocean is still warming. The vast reservoir of subsurface heat that powers El Niño events is still propagating eastward across the Pacific. The full coupling between the ocean and the atmosphere, the phase where feedback loops reinforce each other and the entire system achieves its maximum intensity, is still ahead of us. This means the current situation should not be interpreted as the full impact of El Niño. It should be understood as a preview of what might be to come. This distinction is vital because it fundamentally changes how we assess risk. If this were the peak of the event, the conversation would center on managing an ongoing crisis. But if this is merely the build-up, then the conversation must shift to trajectory, not just where the system is, but where it is heading. At present, that trajectory points toward further intensification. This does not guarantee that the final outcome will mirror the most extreme historical examples, nor does it mean that every region will experience worsening conditions in a simple, linear fashion. Climate systems are notoriously complex, and their impacts are always unevenly distributed. What it does mean, however, is that the baseline from which we are starting is already significantly elevated. In this context, the Everglades fire is not the whole story. It is a marker along a path, a visible and immediate example of how a larger, less visible system is beginning to express itself at the surface. And if that expression has already reached the level of breaking century-scale records before the event driving it has fully developed, then the most important question is not what is happening now. It is what happens next. Part 17. The 1877 Shadow. The year 1877 does not often feature in modern conversations about the climate. On the surface, this makes a certain amount of sense. The instrumental weather records from that era are sparse and geographically limited. Moreover, the world that existed in 1877 looks almost nothing like the one we inhabit today, making direct comparisons difficult. Drawing a direct line from the past to the present is often a complex exercise, as different historical contexts can make comparisons more confusing than enlightening. Yet, the year 1877 consistently emerges in scientific studies on extreme El Niño events. There is a compelling reason for its persistent appearance, one that merits deeper examination. So, it's worth exploring what transpired during that period and why contemporary climate experts in May of 2026 are referencing it now. At a time when the Everglades are burning and the Palmer Drought Index shows its most severe reading in 131 years of record keeping. Based on every available form of proxy climate data, from tree rings and ice cores to historical accounts of its consequences, the El Niño of 1877 to 1878 stands as one of the most severe climate events of the last few centuries. This was not merely a powerful weather event, like a major storm or a regional heat wave. Instead, it represented a profound disruption of the large-scale atmospheric systems responsible for distributing rainfall across the globe. Understanding this distinction is crucial, as it explains why scientists refer to this specific year when trying to define the absolute upper limit of an El Niño's potential impact. The primary effect of the 1877 event was the simultaneous failure of monsoon systems across multiple continents. The Indian monsoon did not arrive. The Asian monsoon failed as well. Across Brazil, rainfall levels plummeted, while severe drought conditions spread throughout sub-Saharan Africa. The vast atmospheric patterns that billions of people and their agricultural lands relied upon for their annual water supply simply collapsed. This wasn't a localized or seasonal anomaly. It was a synchronized global event, with disruptions in the tropics and subtropics driven by a single, massive reorganization of atmospheric circulation that originated in the Pacific Ocean. The historian Mike Davis extensively documented this period in his work on what he termed the late Victorian Holocausts. The term was intentionally provocative, chosen because the outcome of the 1877 monsoon failures was not just a poor harvest, it was a cascading catastrophe. In a world lacking global food supply chains, emergency logistics, modern agricultural technology, or any form of coordinated humanitarian response, the widespread crop failures were a shock the system could not absorb. The famines that ensued resulted in a staggering loss of life. While estimates of the total mortality linked to the climate disruptions of 1878 vary significantly, with figures in the academic literature ranging from 30 to 60 million deaths from famine and disease. The uncertainty in these numbers is both real and important to acknowledge. These figures are the subject of intense debate among historians and climate scientists, who argue over methodology, the challenges of attributing cause between the atmospheric event and the failures of colonial policy, and the reliability of population data from that era. However, one point remains undisputed. Even if one takes the most conservative estimates of the death toll connected to the 1,878 event, it still ranks as one of the deadliest episodes in recorded human history. It was a cataclysm, driven not by war or a pandemic in the traditional sense, but by the failure of rainfall across several continents, all caused by a single El Niño. This raises a sobering question about the immense power of natural climate systems to shape the course of human civilization. It is essential to be precise about what this comparison means in the present day. When scientists invoke 1,877 inches in the context of the 2026 El Niño, they are not making a mortality prediction. They are not suggesting that the events of the 1870s are destined to repeat in the same way. To present their analysis as such would be deeply irresponsible, because the world of 2026 is fundamentally different from the world of 1,877. And these differences are profoundly important to the human side of the story. Today, global food supply chains exist, meaning an agricultural failure in one region does not automatically lead to famine there. We now have early warning systems, advanced meteorological forecasting, and a global infrastructure for humanitarian response. Modern agricultural technologies, from drought-resistant crops and irrigation to synthetic fertilizers, create buffers between atmospheric anomalies and human hunger that were unimaginable in the 19th century. The world's capacity to manage climate shocks has been transformed. So, if the comparison is not about the human outcome, why do scientists still turn to 1,877? They do so because of what that event did to the atmosphere itself. The 1,878 El Niño represents the historical high water mark for what such an event can do to global atmospheric circulation. It is the ceiling in our observational and reconstructed records. This event is the data point that shows us what the physical system looks like when operating at its maximum expression. It demonstrates the level of stress placed on the world's monsoon systems when the Pacific Ocean reorganizes with the greatest intensity the planet has produced in the modern era. When scientists examine the ensemble model forecasts for the 2026 El Niño with median values approaching plus 2.7 degrees Celsius in the Niño 3.4 region, upper end possibilities hitting plus 3.3 degrees, and 100% of the European Center for Medium-Range Weather Forecasts ensemble members pointing to a super El Niño, they reach for the 1,877 event as a benchmark. It is the closest physical analog in the historical record to what those staggering numbers suggest. The comparison is not a prediction of the human consequences, but a description of the physical scale. If the 2026 event does reach the strength that current models are indicating, the physical impacts on global monsoon systems, the disruption to rainfall distribution, and the resulting patterns of drought and flood would begin to approach the physical scale of 1,877. The reference to that year communicates the sheer magnitude of the potential atmospheric reorganization, the degree to which the planetary systems that move water could shift away from the patterns that billions of people and vast agricultural areas are calibrated to expect. The 1,877 comparison is about the physical event, its atmospheric scale, and the absolute ceiling of possibility that the historical record has shown us. The current crisis in Florida offers a compelling, if unsettling, connection to a much larger global story. The fires scorching the Everglades, the 61 simultaneous blazes across the state, and a drought that shattered a 131-year record in the spring of 2026. These are not the main event. They are better understood as signals, early warnings arriving before the phenomenon driving them reaches its climax. The physical loading required to produce an El Niño of this potential magnitude does not happen instantly. It is a gradual process, building over months as subsurface temperature anomalies accumulate and Kelvin waves propagate eastward across the Pacific. The Walker circulation progressively reorganizes, and the atmospheric teleconnections that translate ocean temperatures into weather patterns across North America and the world's monsoon systems develop in stages. This raises a critical question. If what we are witnessing in May 2026 is merely the early atmospheric response to a system still gathering strength, what will its full expression look like? The models point toward December for the peak of the event, which means the conditions currently producing record droughts and fires are just the leading edge. The helicopters dropping water into the burning swamps near Pembroke Pines are real, but they are also harbingers of a main event that is still on the horizon. This is why the year 1877 has entered the modern conversation. It serves as a historical benchmark, representing the outer boundary of what such an event can do to the physical systems that sustain large-scale agriculture and human civilization. The 2026 El Niño is not predicted to replicate the human toll of 1877. Modern infrastructure fundamentally changes that part of the equation. But the comparison is not about the direct human cost. Instead, 1877 provides a stark lesson in the sheer physical scale of disruption that can occur. It is a reminder of how profoundly the global systems that distribute water can be warped when the Pacific Ocean reaches such an extreme thermal state. And the physical process it warns us about is, by all indications, still loading. This brings us to what is known as the regime shift hypothesis. Everything we have covered so far, the fire in the Everglades, the 61 simultaneous wildfires, the 131-year drought record, and Pacific subsurface temperatures running 8 degrees above the historical mean fits, albeit uncomfortably, within a scientific framework developed over decades. Strong El Niño events have happened before. Severe continental droughts and major fire seasons are not new phenomena. The mechanisms are understood, and historical analogues exist. One can point to 1997, 1972, or 1877, and find recognizable versions of what we are currently watching unfold. But some climate scientists believe there is another layer to this story, a factor that could change the fundamental character of what we are experiencing, not just in degree, but in kind. This new element has little to do with the Pacific Ocean directly. Its origins trace back to a specific moment in June of 2023, an event that received minimal mainstream media coverage at the time, but whose implications are now the subject of intense debate in the scientific literature. It is here that the narrative takes a genuinely strange and unexpected turn. Large ocean-going vessels, the container ships, tankers, and bulk carriers that move the physical goods of global trade burn enormous quantities of fuel. The fuel they have historically burned is among the dirtiest in widespread commercial use. This substance, known as bunker fuel or heavy fuel oil, contains high concentrations of sulfur. When it combusts, it releases sulfur dioxide into the marine atmosphere. Sulfur dioxide is a well-known pollutant. It causes respiratory harm in populated areas and contributes to acid rain. Its negative health effects are well documented, and international efforts to reduce these emissions have been driven primarily by those concerns. However, sulfur dioxide in the marine atmosphere produces another, far more counterintuitive effect, one that, from a climate perspective, cuts in the opposite direction. It forms aerosol particles, which are tiny, reflective droplets suspended in the air above the ocean. These particles reflect incoming solar radiation back into space before it can reach and warm the ocean surface. This is the same basic mechanism by which large volcanic eruptions can trigger temporary global cooling. You may have seen photographs of the distinct cloud trails, called ship tracks, that large vessels leave behind them across the open ocean. They appear brighter than the surrounding clouds, precisely because the aerosol particles from ship exhaust seed them with additional reflective droplets. For decades, the global shipping fleet was, in effect, running a planetary-scale geoengineering operation. It was not intentional, but the sulfur emissions from maritime trade were providing a measurable, continuous offset against the warming effect of accumulated greenhouse gases, a partial sun shield hovering over the world's oceans. In January 2020, new regulations from the International Maritime Organization, known as IMO 2020, came into force. They required ships to dramatically reduce the sulfur content of their fuel. The transition was gradual through the initial enforcement period, but by June 2023, compliance had reached a threshold where the reduction in marine sulfur emissions became large enough to measurably alter the aerosol loading of the marine atmosphere. The accidental sun shield started coming down. This is where the work of James Hansen becomes crucial. Over the past 4 decades, Hansen's climate research has repeatedly arrived at conclusions that the broader scientific community initially resisted but later confirmed. Following this regulatory change, he and his colleagues published analyses suggesting a startling development. They proposed that the energy imbalance at the top of Earth's atmosphere may have doubled in the period following 2023 compared to the preceding decade. Let that idea settle for a moment. The claim is not that the imbalance increased or worsened by 10 or 20%, but that it doubled a profound shift in the planet's energy budget. The fundamental measure of our planet's warming is the difference between the solar energy reaching its surface and the heat it radiates back into space. Recent observations suggest this energy imbalance may have abruptly doubled, a development whose precise magnitude remains a subject of intense scientific debate. Some researchers contend that the reduction in cooling aerosols from shipping regulations alone is insufficient to explain the full scope of accelerated warming seen since 2023. They propose that other forces are also at play, including shifts in ocean circulation that redistribute heat in novel ways, and water vapor feedbacks that amplify warming as the atmosphere becomes more moist. This also includes the vast amount of committed warming from past greenhouse gas emissions, which, after a significant lag, might now be fully manifesting in our temperature readings. The scientific community has not yet reached a consensus on how to apportion the observed changes among aerosol reduction, these other powerful factors, and simple natural variability that happens to be trending warm. This uncertainty is a genuine and important part of the current scientific picture. However, some facts are not in dispute, as they are based on direct observation rather than modeling. Since 2023, the global average surface temperature has been running at levels that are not just slightly above previous records, but significantly and persistently higher, shattering old benchmarks. Month after month has either set or neared the record for the warmest ever observed for that time of year. Simultaneously, the heat content of the world's oceans, measured at depth, has climbed to new highs. Arctic sea ice extent has continued its decline, and atmospheric water vapor itself, a potent greenhouse gas, has been measurably above its long-term trend. The data clearly indicates that something fundamental shifted after 2023, even as the exact explanation is still being pieced together. To explain this shift, a group of researchers is now putting forward a compelling hypothesis, though it is crucial to recognize this as an area of active inquiry, not a settled conclusion. The proposal is not that the climate has changed direction. Its consistent warming trend for decades is undisputed by any serious scientist. Instead, the hypothesis suggests a change in the rate times of warming. This acceleration, they argue, is driven by a powerful combination of factors. First, The reduction in aerosols has removed a long-standing cooling effect, unmasking the true extent of underlying warming. Second, the accumulated, committed warming from historical emissions is now being expressed without that cooling offset. Finally, positive feedbacks, such as those from water vapor and reduced ice albedo, are amplifying the initial push, causing warming to exceed what the initial drivers alone would produce. This framework attempts to weave together multiple lines of evidence into a single, coherent explanation for the recent anomalies. If this hypothesis proves to be even partially correct, the implications would be far-reaching, extending well beyond the current El Niño event developing in the Pacific. It would suggest that the entire planetary climate system is now operating with a greater amount of available energy than it was just a decade ago. More energy in the system translates directly into more intense and more persistent atmospheric anomalies. This means that the kind of stubborn blocking patterns that locked the atmosphere over the southeastern United States this spring, leading to a 131-year drought record, could become more common and more difficult to break. It also means that heat dome events could grow more intense, while the mechanics of flash droughts, the dangerous feedback loops between high temperatures and soil moisture that can parch a region in weeks, could operate with greater speed and aggression. From this vantage point, the 131-year drought record is not merely a statistical outlier, a rare event at the far end of a stable probability curve. It could instead be one of the first clear signals that the curve itself has shifted. This raises a profound question. Has the entire range of outcomes the climate system can generate expanded in the direction of more extreme warmth? The records being shattered now might not be a result of simple bad luck within the bounds of normal variability. Instead, they could be happening because the underlying system that generates these outcomes is fundamentally different from the one that produced the climate data of the previous 130 years. It must be stressed that mainstream climate science has not yet formed a consensus around this idea. The regime shift hypothesis has serious proponents with distinguished credentials, but the evidence is still being compiled and analyzed. Alternative explanations are still under rigorous evaluation, and the scientific process of distinguishing a true signal from the noise within a complex planetary system inherently takes time. What can be stated with confidence, however, is that the pattern of extreme events observed since 2023 is not easily explained by simply extending the prior trajectory forward and accounting for normal variability. Something has changed. The work now is to determine precisely what changed and by how much. This brings the global picture back to the local level, to the smoke over Pembroke Pines and the helicopters flying over the Everglades. It brings us back to the sawgrass burning in a landscape that, based on any prior understanding of this ecosystem, should be far too wet to burn in May. The fires in the Everglades are burning at the confluence of all the factors we have discussed. A developing El Niño is injecting unprecedented thermal energy into the atmosphere, reorganizing global circulation in a way that suppresses rainfall across the continental United States. This is layered on top of a continental drought structure, built by months of locked atmospheric blocking patterns that resist the normal weather changes that would typically break them apart. All of this is occurring within a climate system that may be operating at a fundamentally higher energy level than at any point in the modern instrumental record, making it capable of producing and sustaining extremes that historical baselines would have deemed improbable. And it is happening in a local ecosystem, the Everglades, whose engineered water management infrastructure was designed for a range of conditions that the reality of 2026 has now decisively surpassed. The 131-year drought record is the single number that tells you something qualitatively different is happening. A record that stands for over a century does not fall because of normal, random fluctuations. It falls because something about the system that generates those outcomes has fundamentally changed. The reduction in aerosols is one candidate for that change. The accumulated committed warming is another. The positive feedbacks now fully expressing themselves are a third. The most probable explanation is that it is some combination of all of them, with a strong El Niño event layered on top of a baseline that is already running hotter and is more energetic than at any other point in the modern record. Ultimately, the evidence points toward a system that is no longer operating within its historical bounds. The flames are where a vast, complex process becomes tangible. They are the concrete evidence of a system failure that satellites can photograph, that emergency responders can fight, and that residents can smell through sealed windows. But the system that generates these fires is itself invisible. It spans oceans and atmospheres, operating on a planetary scale. Its cycles unfold over timelines far longer than a news report, a single fire season, or even a decade. And as of May 2026, that system is still evolving. This is the story of why this particular fire matters. First, a necessary dose of perspective. The Max Road Miramar fire is not the largest blaze in Florida's history, not by a significant margin. Even the railroad fire, burning concurrently just miles away, does not set any records for sheer acreage. And while the 2026 Florida fire season arrived with dramatic and early intensity, it is not projected to eclipse the vast devastation of 1998 or 2007. If one were to present the burn statistics from the 11th of May 2026 to a panel of fire historians, many would acknowledge that, in terms of raw size, Florida has indeed weathered worse. They would be factually correct. So, this raises an essential question. If not for its size, why does this event demand our focus? The significance of this fire is not measured in acres. Its true importance lies in the date, the context, and the uniquely revealing set of circumstances that had to align for it to even be possible on the 11th of May, 2026. When you trace that chain of conditions, following the evidence from one link to the next, the narrative ceases to be about a simple fire. Instead, what emerges is a powerful diagnostic signal, a clear message about the state of the planetary system that produced it. The story begins in the soil. For a wetland to be actively burning in the second week of May, its soil moisture must have plummeted to between the 5th and 20th percentile for that specific time of year. This is no minor dry spell or a brief pause between rain showers. A 5th percentile reading indicates that the ground is drier than it has been in 80 to 95% of all previously recorded years. For nearly every year on modern record, the Everglades soil was wetter at this point in May. This is a profound departure from the norm. You cannot reach 5th percentile soil moisture in early May after just a single dry week or even a dry month, a number that low represents an accumulated deficit, a historical record of months without adequate precipitation. It speaks to a prolonged period of missing rainfall and atmospheric conditions that prevented the essential recharge of the water table. This shallow water is what normally keeps the ecosystem's peat layer saturated and its sawgrass too damp to sustain a fire. In this light, the soil moisture reading from May 2026 is not merely a weather observation. It is a history written into the earth itself. It is the atmosphere's own record of its behavior. Every week of below-average rainfall, every week of increased evaporative pressure, and every week that the region's vital afternoon thunderstorms failed to form is encoded in that single number. The soil, in effect, becomes a ledger. And that ledger clearly shows that the atmosphere had been failing this ecosystem long before any spark was introduced near Chrome Avenue. Now, consider the fuel. For the fire season to be running a full 6 weeks ahead of schedule, and for the rapid wind-driven spread observed by emergency managers on May 10th and 11th to be physically possible, the vegetation had to be exceptionally dry. The plants across the affected landscape had to be capable of carrying fire with an intensity normally seen only under the peak conditions of late June or July. The state of the fuel tells its own story of a system under stress. The moisture content of vegetation, from trees to sawgrass, does not fluctuate rapidly. It is the result of a balance struck over weeks and months between the water supplied by rainfall and the moisture drawn out by atmospheric demand. When fire behavior analysts discover fuel moisture levels consistent with midsummer, they are not observing a localized fluke. They are reading a record of the entire preceding season, physically encoded in the plants themselves. The plants offer a direct physical measurement of the atmospheric history they have endured. They cannot mislead. When the sawgrass in the Everglades is dry enough to carry a fast-moving fire in early May, it is because the atmospheric conditions of the prior months made it so. The fire's behavior becomes the ultimate evidence. Its rapid rate of spread, its wind-driven advance, and the failure of standard firefighting tactics to achieve containment are all ways the ecosystem is reporting back on the conditions imposed upon it. The fire is a symptom of a deeper imbalance. Zooming out further reveals an even more troubling picture. 61 fires were burning simultaneously across a single state. 49 of Florida's 67 counties were under active burn bans. Over 2,000 separate fires had already been recorded year to date by early May. A single drought in one wetland creates local fires. A bad week of weather in one corner of the state produces fires in that corner. That is the kind of activity Florida's emergency infrastructure is designed to handle routinely, season after season, without becoming a national event. But 61 simultaneous fires across 49 counties represents something categorically different. It is the signature of a condition that is neither local nor temporary. It signifies that across the entire state, wherever a normal source of ignition might occur, a lightning strike, a downed power line, a spark from equipment, or a carelessly tossed cigarette, the conditions on the ground are now extreme enough to turn it into an active blaze. Under normal circumstances, the limiting factor in the fire equation is not the source of ignition. Sparks and potential ignitions are a constant presence. The true limiting factor is typically the fuel and moisture conditions, which determine whether a spark fizzles out or grows into a fire. When 61 fires are burning at once, almost every ignition now results in a fire because there is nothing left in the system to stop it. This is not a collection of 61 individual events. It is one atmospheric condition, expressing itself through 61 simultaneous emergencies. And now, we must place this statewide crisis into its planetary context. All of this is unfolding against the backdrop of a developing El Niño, an event whose underlying conditions are already extraordinary. In the Pacific, subsurface ocean temperatures have surged to levels that surpass anything in the modern observational record. Forecast models suggest that if this El Niño reaches its projected peak, it could rank among the most powerful such events ever documented. Yet, this is only the beginning. As of late May 2026, the El Niño has not yet peaked. It remains in its formative stage, with the full force of its atmospheric influence still months away. This context is critical for understanding the severity of what is already happening. The United States is experiencing a cascade of record-breaking events, the lowest national precipitation in 131 years and the worst ever reading on the Palmer Drought Severity Index. A staggering 60% of the continental U.S. is simultaneously in drought. But these are not the direct consequences of a mature El Niño. Instead, they represent an early atmospheric reaction to a Pacific Ocean that is still gathering its strength. To grasp this distinction, we can borrow a concept from medicine. The presenting symptom. When a patient visits a doctor, they describe something tangible, a fever, a rash, a pain that prompted their visit. While this symptom is real and requires attention, an experienced physician knows it is rarely the fundamental problem. It is merely the surface expression of a deeper process. A fever, for instance, is a symptom. The underlying infection is the actual problem. Treating only the fever ignores the root cause, allowing the deeper issue to persist. In this analogy, the Max Road Miramar fire is a presenting symptom. Even the 131-year drought record is just a more profound symptom of the true issue. The actual problem is a convergence of atmospheric, oceanic, and potentially systemic forces, aligning in 2,026 inches, a way never before seen in modern records. This configuration involves a developing El Niño of potentially historic scale, superimposed on a climate system that some scientists believe entered a new energy state after 2023. This new state is manifesting through persistent atmospheric blocking patterns that have starved the southeastern United States of moisture, creating a deficit of record-breaking severity. The region's engineered water management systems are simply no match for an atmosphere that has ceased to deliver rain. The fire in the Everglades did not create these conditions, it merely exposed them. This is what the leading edge of a planetary scale convergence looks like when it arrives in a community. It is not an abstract concept on a temperature graph or a color-coded map. It is the smoke hanging over Pembroke Pines, the air quality alerts in Miramar, and the helicopters dropping water into a burning swamp. It is families sealing their windows against the air in their own neighborhoods on a Monday in May. The impact is concrete, visible, and undeniable. The fire's true significance is not its size, as Florida has witnessed larger blazes. Its importance lies in what had to be true for it to exist at all. In this specific place, on this specific date, during this particular alignment of forces. A fire in a wetland in early May, fueled by the atmospheric precursors of an El Niño that is already rewriting record books before it has even fully arrived. This is the opening signal of a system that is still loading. To understand this sequence, it is more instructive to trace the chain of events forward from the ocean, rather than backward from the fire. The process began in the western tropical Pacific, in the warm pool near Indonesia and the Philippines, where heat had been accumulating for months and years. During the winter and spring of 2026, the trade winds that typically hold this warm water in the west began to weaken, a classic precondition for an El Niño. In April, this process was dramatically accelerated when 3 simultaneous tropical cyclones created a westerly wind burst of unusual strength. This burst injected immense momentum into the ocean's surface, generating downwelling Kelvin waves that began to travel east across the equatorial Pacific. These waves pushed a mass of warm water eastward, causing subsurface temperature anomalies to reach an unprecedented +8 degrees Celsius in some areas, exceeding anything observed in prior El Niño events. As the ocean reorganized itself, it began to alter the Walker circulation, the vast atmospheric engine that links sea surface temperatures in the Pacific to weather patterns around the globe. This reorganization suppressed rainfall over the continental United States through a phenomenon known as the Pacific North American teleconnection, which shifted the position of major ridge systems over the continent. The Bermuda High, a semi-permanent zone of high pressure, strengthened and expanded westward, effectively blocking moisture from reaching the southeastern United States. Amplified Rossby waves contributed to the persistence of these blocking patterns, making them resistant to normal weather fluctuations. At the same time, flash drought mechanisms, feedback loops between high temperatures, low soil moisture, and high evaporation rates, dramatically accelerated the drying of the landscape across the southeast, outpacing the ability of drought monitoring systems to keep up in real time. The consequences for the United States were severe and widespread. From January through March 2026, precipitation across the contiguous U.S. totaled just 4.79 inches, the lowest amount since record-keeping began in 1895. The Palmer Drought Severity Index, a measure of long-term drought, hit 7.84 on a national scale, the most extreme reading ever recorded. 60% of the country fell into drought conditions, a figure 3 times the historical average. Florida was hit particularly hard, with 99% of the state experiencing drought and nearly a quarter falling into the exceptional category, the system's highest level of severity. This extreme dryness set the stage for a devastating fire season. In Florida, it arrived 6 weeks ahead of schedule. Burn bans were enacted in 49 of the state's 67 counties as the number of fires for the year surpassed 2,000. At one point, 6 active fires were burning simultaneously across the state. On May 10th, the Max Road Miramar fire ignited. It exploded from 80 acres to 4,800 acres in a matter of hours, sending helicopters over Pembroke Pines, filling living rooms in Miramar with smoke, and reducing visibility on Alligator Alley to near zero. Every link in this causal chain is documented, from the initial warming in the Pacific Ocean to the atmospheric reorganization over a continent, all culminating in a fire in South Florida. Yet, what this complete chain of events does not resolve is the most unsettling question of all. The El Niño, the primary driver at the start of this entire sequence, has not yet reached its peak. The system is still building toward whatever it is going to become. Current model ensembles project a median warming of plus 2.7 degrees Celsius for the peak period from December to February, with some upper-end forecasts reaching plus 3.3 degrees. The European Centre for Medium-Range Weather Forecasts, ECMWF, is particularly stark, with every single one of its ensemble members pointing toward a super El Niño event. To find a potential parallel in the climate record, scientists must look back to the years 1877 and 1878, an analogue that offers a sobering historical context. The process of energy accumulation in the Pacific is far from over. The westerly wind burst in April, which accelerated the buildup of subsurface heat, was merely one step in a continuing sequence. This raises a critical question. What will unfold between May and December as this El Niño reaches its full maturity? As the deep ocean heat rises to the surface and the water circulation reorganizes, what becomes of the already exceptional drought conditions? What will happen to a fire season that is already 6 weeks ahead of schedule, or to the peat deep beneath the Everglades, which is at risk but not yet, to our knowledge, burning? Simultaneously, we must consider the opposite extreme of El Niño's impact, the areas that often face catastrophic rainfall, the Pacific coast of South America, regions of East Africa, and the Indian subcontinent have all historically experienced immense human suffering when strong El Niño events disrupt monsoon patterns. As of now, these questions remain unanswered. The climate is not a simple, deterministic system where outputs can be calculated with precision. There are profound uncertainties about how powerful this El Niño will become, how its effects will be distributed across the globe, and how it will interact with the potential for a broader regime shift that some researchers have identified. The fire ravaging the Everglades is a tangible, immediate event. It is something that can be seen from orbit. Its smoke smelled in the community of Miramar, and its suppression efforts watched on news footage of helicopters. The reality of the fire is concrete and local. In stark contrast, the system driving this event is anything but. It is a phenomenon of oceanic and continental scale, operating on timelines that stretch from seasons into decades. This larger system doesn't manifest as smoke plumes and helicopters. It appears as numbers in spreadsheets and as anomaly maps that require specialized expertise to fully comprehend. Yet, it is crucial to understand that the connection between the abstract data and the visible smoke is undeniably real. A causal chain links the depths of the Pacific Ocean to the burning sawgrass of Florida, and that chain is still accumulating tension. After tracing this story from the fire back to the ocean, the question that should linger is not what caused the blaze in the Everglades. That answer has been provided. The more pressing question is, what will December look like? If a developing El Niño, not yet at its peak, can contribute to conditions in May that result in 4,800 acres burning, near zero visibility on Alligator Alley, and air quality alerts in Miramar, what can we expect from the full expression of this system? What will be produced when the ocean finally reaches the temperatures its current trajectory suggests? There are no certain answers. The climate models show disagreement on the ultimate magnitude of the event. Scientists debate the pace at which it will unfold, and the historical analogues we turn to are imperfect, drawn from a world that was fundamentally different from our own. The only thing that is not in doubt is that the system we have tracked, from the Florida sawgrass to the subsurface Pacific, has not yet finished building its strength. The fire in the Everglades acts as a signal, much like a single tremor is a signal before a major earthquake. Its significance is not in predicting the exact magnitude of what might follow, but in what it reveals about the fundamental state of the system producing it. This event tells us that the system which created this fire in May 2026 is not in equilibrium. It is a system under immense stress, and the source of that stress is still intensifying. The fire itself is just the surface expression. Beneath it lies peat that has stored 5,000 years of atmospheric carbon, now facing conditions that threaten its stability for the first time in its existence as a landform. Beneath the peat is a managed water system, struggling to operate under pressures it was never designed to withstand. And beneath that engineered system is a natural ecosystem, whose ability to adapt was calibrated for a range of conditions that the atmosphere of 2026 has already surpassed. At the very bottom of this cascade, driving it all, is the ocean. It is still loading, relentlessly pushing warmth eastward in vast waves of displaced heat, a process that began with 3 tropical cyclones and a westerly wind burst in the western Pacific, and is set to arrive in its full force sometime between now and the end of the year. The Everglades are on fire. This is the headline, the presenting symptom, the local and documentable fact. But the data insists that we ask a much larger question, one the headline itself does not pose. What kind of planet is it that produces a burning wetland in May as merely a preview of conditions still building toward their peak? We are witnessing the beginning of a significant event, though we do not yet know its ultimate duration or intensity. The models provide us with a range of possibilities. History offers a sobering, if imperfect, analog. The ocean indicates a clear direction of change, and the fire in the Everglades gives us a window. Through that window, if one looks closely, it's possible to see the faint reflection of what is yet to come.